China has constructed hotels that challenge every traditional rule of building design. Not just one or two, but 18 remarkable properties. Structures that forced architects to rethink standard approaches and made engineers reconsider what was physically possible. These include buildings that extend outward as they rise, towers with openings carved through them, castles along coastlines, and venues buried deep underground. You are about to discover how they achieved it. The first one suspends a Ferris wheel between two towers hundreds of feet in the air. Studio City, Macau. Imagine standing in Macau, looking upward at two gleaming towers connected high above the ground by a golden figure-8 shape. It is a Ferris wheel spinning 427 feet in the sky, and its placement defies easy explanation. Constructing the towers themselves was complex enough. The real difficulty involved mounting a 17,000-ton observation wheel between them while both structures were already complete. The wheel does not rest on the ground. It attaches directly to the buildings at mid-height, with passenger cabins rotating through both loops of the figure-8. Steel bridge elements extend from each tower and meet in the center to support the wheel. Connection points were engineered to manage shifting loads as the 28 cabins move during operation. Each support beam incorporates slight flexibility to absorb motion without stressing the towers. The wheel integrates into the overall structural system, secured by tension cables and hydraulic dampers. They created a Ferris wheel that floats in the air and keeps turning. That project served as preparation for what followed. MGM Macau. Entering the Grand Pra reveals a striking sight overhead. A large glass wave curves gracefully across 82 feet of open space. No supporting columns interrupt the area below. Thousands of glass panels form a flowing ceiling that appears frozen in motion. The task was straightforward yet daunting. Glass carries substantial weight. This ceiling weighed hundreds of tons and needed to span the entire public area without any visible supports. A single error could have sent the structure crashing down. Engineers created a tension cable network woven into the curved framework. Steel cables stretched like taut strings along the edges and through the assembly. Each cable spread weight toward the outer walls, preventing concentration in any single area. The glass panels worked together as an interconnected system, with each piece supporting others through calculated forces. The frame's deliberate curvature redirected downward pressure outward. You stand beneath hundreds of tons of glass held in place purely through physics and precise design. MGM Cotai. Stepping into the lobby presents a view that seems structurally impossible. The building rises in stacked sections, resembling shipping containers piled unevenly. Each level shifts position from the one below, with some blocks protruding outward and others receding. The challenge involved constructing a tower that avoided straight vertical stacking. Each offset created cantilevered portions with open space underneath. Standard methods rely on direct downward load transfer through columns. This design pushed weight sideways. Massive steel transfer trusses at every shift point caught the overhanging sections and redirected forces to columns below. These horizontal beams, some spanning multiple stories, managed eccentric loads. The central reinforced concrete core provided stability but required assistance. Steel outriggers extended from the core into protruding areas, functioning like braces against the cantilevers. Where sections pulled inward, tension cables through floor slabs drew overhanging parts back toward the center. Each transition demanded unique calculations. No two shifts used identical solutions. They created a tower that appears on the verge of collapse, yet the engineering ensures perfect stability. Grand Lisboa. This building widens as it ascends. The base measures 295 feet across while the top expands to 427 feet, reaching 853 feet in height. It resembles a lotus flower opening upward in steel and concrete. Every level violates a fundamental construction principle: avoid expanding outward while building upward. Traditional towers narrow to manage wind forces and maintain balance. This one grew broader with height. The core, a reinforced concrete cylinder 30 feet in diameter, runs the full height as the central support. Radial steel trusses extend outward from it at each floor, lengthening as the structure rises. These form three-dimensional frameworks, some several stories deep, handling both cantilevered floor loads and twisting forces from wind. Each truss transfers weight back to the core through post-tensioned cables pulled to extreme tightness, converting compression into tension. At the uppermost levels, a tuned mass damper, weighing hundreds of tons, swings on pendulums to counteract sway during strong winds. They constructed a flower that blooms as it grows, with engineering preventing it from tipping. Sunrise Kinsley Hotel. A golden ring stands 325 feet tall on its edge along the shore of Yangji Lake. A flawless circle rises from the water's edge. No wider base, no gradual taper, just a continuous loop that looks as though a giant coin rolled to the lakeside and remained upright. The obvious difficulty was making a circular form stand vertically. The shape wanted to topple in multiple directions. Wind created pressure on one side and suction on the other. Without a stable foundation, every calculation battled geometry. Two structural cores embedded at opposite points within the ring served as hidden pillars. Positioned where the ring meets the ground and curves overhead, they created anchor points 180 degrees apart. Steel framework followed the circle's curve, forming a rigid tube. Internal diagonal bracing crisscrossed like bicycle wheel spokes to distribute forces around the loop. The foundation extended 100 feet into bedrock, with angled piles resisting both vertical and sideways movement. The ring locks firmly into the earth rather than simply resting on it. They built a symbol of infinity and gave it solid footing. Wynn Macau. A curved glass tower bends gracefully like a sail caught in the breeze. The facade forms a continuous wave of glass panels, each angled uniquely, wrapping the crescent-shaped building. At 51 stories and 600 feet tall, every surface reflects harbor light. The curve itself created the primary difficulty. Flat glass installs easily on grids. Curved facades demand custom cutting for every panel, precise angle calculations, and mounting points designed for varying loads. The crescent form meant direct wind pressure on one side and suction on the other. Glass had to withstand both without excessive flexing. A steel subframe behind the glass formed a three-dimensional framework following the curve, with brackets positioned at exact coordinates for each panel. Every bracket accommodated thermal expansion. Glass moves with temperature changes, and rigid fixing would cause shattering. Panels used laminated construction so that if one layer failed, others maintained integrity. Structural silicone provided flexible yet strong edge sealing. The entire facade suspended from concrete floor slabs above, with each level supporting glass weight below and transferring loads to the core. They wrapped a crescent form in glass and engineered it to withstand typhoons. Galaxy Macau. Entering the diamond lobby reveals a 50-ton chandelier suspended above 21,500 square feet of open space. Hidden steel trusses above the ceiling support it, with bundled cables connecting to an internal framework maintaining balance. Outside, 3 golden towers rise from a shared base at varying heights. Curved gold-toned glass wraps the facades. The structural difficulty involved supporting 3 separate towers above vast column-free areas used for lobbies, casinos, and convention spaces. Transfer trusses at the podium roof level, some 3 stories deep, redirected tower loads horizontally before channeling them through perimeter columns. Each tower's reinforced concrete core provided lateral resistance. Outrigger trusses at mechanical floors linked cores to outer columns, stiffening against typhoon forces. Curved glass attached to steel subframes with brackets allowing thermal movement. A massive reinforced concrete mat foundation spread the combined weight of all 3 towers. They constructed 3 distinct towers on one base, each unique yet all stable. The Parisian Macau. The Eiffel Tower rises from the hotel entrance at 492 feet tall, half the scale of the Paris original. Its iron lattice anchors to the building's foundation, serving as the complex's centerpiece. Supporting such a massive tower as part of the hotel structure posed significant challenges. 7,000 tons of steel framework needed to transfer its load through casino levels, lobbies, and occupied spaces down to bedrock. The tower represented substantial dead weight pressing on everything below. A reinforced concrete foundation platform distributed the tower's load across the site. Steel framework replicated the Eiffel's diagonal members, forming the iconic taper with horizontal platforms at observation levels, all bolted together. The base integrated directly into the casino floor. Isolated load-bearing columns beneath the tower transferred weight straight down, separate from columns supporting hotel areas. The foundation extended deep with pile groups driven into bedrock to manage concentrated loads. They constructed half an Eiffel Tower atop a hotel foundation and reinforced the ground sufficiently to support it. The Venetian Macau. Inside 10.5 million square feet, the seventh largest building on Earth, you find a casino, shopping areas, convention spaces, hotel towers, and indoor canals with gondolas beneath a painted sky. It recreates Venice within a single structure. The difficulty involved spanning vast column-free areas. Casinos required open floors. Shopping corridors needed clear sightlines. Canals filled with water sat on upper levels not typically designed for such loads. Post-tensioned concrete slabs, with cables pulled tight through the concrete, enabled thinner floors to cover longer distances without columns. Steel trusses bridged gaming areas, some spanning over 200 feet. For canal levels, reinforced floors handled hundreds of thousands of gallons. Waterproof membranes sealed beneath decorative surfaces. Structural concrete canal bases supported water weight and gondola movement. Hotel towers rose from the podium, with loads redirected through transfer structures around open spaces below. They built Venice indoors, complete with canals, towers, and piazzas under one roof. Hotel Eclat Beijing. 20,000 individual glass pieces cover the facade. Not standard windows, but unique glass sculptures, each varying in size, angle, and shape. A cubist composition frozen in dramatic form. Mounting 20,000 distinct pieces created the primary challenge. No two were identical. Every angle required custom calculation. Every bracket was engineered separately. The entire surface needed to withstand wind forces on protruding elements. A steel subframe backed the facade, forming a three-dimensional grid attached to concrete. Each glass piece received a custom bracket designed for its specific orientation and weight. Computer modeling calculated loads for every element, including wind pressure, glass weight, and thermal expansion. Brackets incorporated flexible connections allowing movement. Glass expands and contracts with temperature changes. Rigid fixing would cause breakage. Structural testing verified wind performance on the faceted surface. Irregular angles generated turbulence, unlike flat facades. They covered a building with 20,000 sculptures, each engineered individually. The Castle Hotel Dalian. On China's coastline stands a full-scale Gothic castle, not merely inspired by European examples, but recreated with towers, turrets, stone walls, and spires. It appears transported from medieval Germany, yet engineered for earthquakes and typhoons. Replicating historic architecture in a modern seismic zone presented difficulties. Traditional Gothic castles relied on massive stone walls for support, but stone lacks flexibility and cracks under stress. Coastal China requires structures that withstand earthquakes and strong winds. A steel skeleton hidden inside period-appropriate stone provided the solution. Steel frame columns, beams, and lateral bracing handled all structural demands. Stone served as cladding, attached with anchors allowing independent movement. During seismic events, steel flexes while stone moves with it without bearing primary stress. Spires and towers, traditionally solid stone, became composite forms with steel cores wrapped in stone exteriors. Foundation piles reached deep into bedrock beneath coastal soil, anchored against vertical loads and lateral forces. They constructed a medieval castle using a modern internal framework, with stone on the outside and steel within. You have now seen 18 hotels that redefined construction boundaries. They cantilever outward while rising, create voids through towers, build downward into quarries, suspend over water, and make spherical forms functional. China did not merely test engineering limits. They moved beyond them entirely.